and kind of review some of the things that we've talked about the last few days. Okay, the first thing that I want to discuss or recap with you is difference between a solvent and a solute. So our quiz practice number 1 says, in a saltwater solution, why is water the solvent and why is salt the solute? Well, we've mentioned before that a solute is the substance that actually dissolves. And I know that if I pour salt into the water, the salt dissolves. The water does not dissolve, it is only the salt. So the reason that salt is the solute is because it is dissolving and because it is typically in the lesser amount. So as far as water being the solvent, the water is actually dissolving the salt. The salt is dissolving into the water, and water is found in the greater amount. Okay, so a couple things that help distinguish between a solvent and a solute. Number 2, write the molarity formula. Well, our molarity formula is capital M for molarity equals the amount of moles of your substance divided by your volume. And remember that our volume is always measured in liters. Now, if I want to rearrange that equation, and let's say I want to get volume by itself, then that equation would look like this. It would say, I'll write it over here to the left. It would say volume equals moles over molarity. And if I want to solve for moles, moles is molarity times volume. And both of those two equations all stem from my original. Okay, so let's practice using that calculation. Number 3 says, how many liters of water are required to create a 2.5 molar solution with 0.75 moles of NaCl? So let's look and see what we have here. We've got 2.5 M, and I know that measures molarity. I've got 0.75 moles, which measures moles. And it's asking me to figure out how many liters of water. So it's asking me to solve for volume. I need to know how much water I have. Okay? So I can use my molarity formula, or I can use the one that's rearranged since we already know how to rearrange it. And that one says that volume equals moles divided by molarity. So since I've already identified everything that's given to me and what I'm solving for, I'm going to plug them into my equation, where my moles is 0.75 and my molarity is 2.5. And when I divide those two together, I get 0.3. 0.3 liters. All right, moving on to the next one, number 4. Number 4 says, which solution is more concentrated? And it gives you a hint here to calculate the concentration of each. So in A, it says A solution with 2 moles dissolved in 1.5 liters. B says a solution with 1.5 moles dissolved in 0.65 liters. So we need to figure out the concentration of A and the concentration of B to figure out which one is more concentrated. So let's start with A first. In A, I'm given the number of moles, which is 2, and I'm given 1.5 liters, which measures volume. So I need to figure out molarity. And we said already molarity equals the number of moles divided by volume. So my molarity is 2 divided by 1.5 liters, giving me a molarity of 1.3. Okay, if I look over at solution B, B gives me 1.5 moles and 0.65 liters. That's my volume. So using the same equation, molarity equals moles divided by volume. The amount of moles is 1.5, and the volume is 0.65 liters. And when I calculate that, I get 2.3. So when I compare solution A to solution B, solution A gave me 1.3, solution B gave me 2.3. So the more concentrated the solution is, the higher the number is, the higher my molarity will be. Therefore, B is a greater concentration. All right, let's look up at number 5. Number 5 wants me to find the molarity of a solution that has 11.5 grams of sodium hydroxide dissolved in 0.75 liters of water. And it gives you a hint here to find the molar mass of sodium hydroxide, and it's 39.997. Okay, so let's look at what we have here. Okay, it gives me grams, and grams measure mass. Okay, it also gives me 0.75 liters. Liters measures volume. And it's asking me to find molarity. So I want to try to find molarity. Well, the only way that I can find molarity is if I use my molarity equation, which is moles divided by volume. So when I look at everything that I've got, in order to calculate molarity, I need moles and volume. But according to my problem, I've only got volume. I've got mass, and mass is not the same as moles. So I can't use this equation yet. So I need to think of a way that I can convert this mass into moles. And for that, I'll need to set up my T-chart. So step 1 will be to set up my T-chart with my mass. So I'm given 11.5 grams of sodium hydroxide. So I'm going to rewrite down here, the bottom right, grams of sodium hydroxide. And if I've got grams, I've got to write moles with it. This is a molar mass conversion. And anytime I've got grams, that means that this is a 1. So your hint said that the molar mass of sodium hydroxide is 39.997. So it's telling you the molar mass of sodium hydroxide, 39.997. So in other words, if you took the mass of sodium plus the mass of oxygen plus the mass of hydrogen, you would get 39.997. So after I calculate this, I get 0.287 moles of NaOH. Now, that's just the first step in finding my answer. My second step is to take what I just found, the moles, and plug it into my equation that we wrote up here. So, molarity equals moles divided by volume. Well, we now found, using our conversion up above, that we have 0.287 moles, and in our problem, it told us that we had 0.75 liters. So when I calculate my molarity, I get 0.38. All right, and moving on to the last one, number 6. Number 6 says, what will be the molarity if you add 75 milliliters to 355 milliliters of a 7.50 molar potassium hydroxide solution? Okay, so let's identify the information that's given to us. It says 75 milliliters. I know that milliliters measures volume. 355 milliliters. Again, milliliters measures volume. We got 7.50 M. Capital M measures molarity. And it says, what will be the molarity? So it's asking you to find molarity. Molarity is unknown. So we've established our volumes and our molarities. Now we need to figure out which ones are in the same solution. So remember, yesterday we mentioned that if that word of appears, chances are the two numbers that are on either side of are in the same solution. So I've got 355 milliliters of 7.5 molar KOH. That means these two are part of the same solution. So I'm going to label these both with the same number. I'm going to give this a V1, and this will be M1. So if this is V1, then this has to be V2. And if this is M1, then I must be trying to find M2. Okay, so I'm going to start with my equation. And my equation says V1, M1 equals V2, M2. Now, before I can start plugging things in there, one other thing that we mentioned before is that anytime you've got milliliters, they have to be converted to liters. So I'm going to take 75, and I'm going to move the decimal 3 places to the left. It would be 1, 2, 3, or in other words, take 75 and divide it by 1,000. Either way, I get 0.075 liters. And if I do the same thing to 355 milliliters, if I move the decimal 3 places, 1, 2, 3, or 355 divided by 1,000, I get 0.355. So now I've got my volumes in liters. Now I can plug everything in. So V1, we said, was 0.355. M1 is 7.50 equals V2 is 0.075 and M2 is unknown. So if I want to get M2 by itself, it's my unknown, it's my X, it's my variable. If M is being multiplied by 0.075, I need to do the opposite to get it over on the other side. So I need to divide. So I'm going to divide this side by 0.075. This side by 0.075. These cancel out. And that leaves me with 0.355 times 7.5 divided by 0.075 equals M2. And when I plug everything into my calculator and solve for M2, I get 35.5 molar solution. Okay, so these are the sorts of things that are going to be on your quiz tomorrow. I would recommend that you look over this as well as the notes from the last couple days to help you prepare for our quiz, tomorrow. So let's look on to the back side. We're going to talk about water and rates of dissolution. Okay. So what gives water its unique properties? Well, we've already talked before in previous units that water is a polar molecule. Okay, so there is a pool of electrons from the oxygen, making the oxygen slightly negative and the hydrogen slightly positive. So this molecule is polar. So that's a unique property. So remember that the oxygen and the hydrogen, they share electrons. It's a covalent bond. But oxygen is way more electronegative. Oxygen is further on the right of the periodic table than hydrogen, so it is more electronegative, which means it pulls on the electrons a lot more. So that gives oxygen its slight negative charge, and hydrogen has its slight positive charge. So when an atom has areas of partial charges, it's called a polar molecule. So the shape also contributes to some of the water's properties. The name of the water's shape, if anyone can remember, I'll give you a second to guess. The shape of this molecule, if you just look at it, it's not linear. It's like it was a linear model, but then someone grabbed it and bent it, giving it its bent shape. Okay, so this is an example. This shows us a polar water molecule. Okay, if I look at my hydrogen bonds here on the right, if I look at this diagram here, I've got ice and I've got water in the liquid form. So what I'm looking at here is my hydrogen bonds. In ice and hydrogen bonds when they are a liquid. And what you notice is that in ice, when they are frozen, they're less dense. But in water, they are more dense, which means they are closer together. Which is why when you put ice into a cup of water, ice floats because it is less dense than a liquid. So due to these charges, these partial charges, it gives it other unique properties. So which substances can dissolve in water, or which substances can water dissolve? So here's a rule. In order to figure out which substances can dissolve in water, just remember, like dissolves like. So that means, based off of water's properties, water can dissolve polar molecules, because water itself is polar, and it can dissolve ionic compounds because water is also ionic. It's got a charge. What water does not dissolve? Well, if it dissolves polar molecules, then that means that it does not dissolve nonpolar molecules. Substances such as oils, wax, fats, these molecules do not have a partial charge, which is why they do not dissolve in water, which is why if you've ever poured or mixed oil and water, you notice that they will always separate. So how does water dissolve substances? So water's partial charges pull apart the solute. Whatever solute is added into the water, the partial charges pull it apart. So what you look at here is you're looking at sodium chloride, NaCl. Sodium, remember, has got a positive charge. Chlorine's got a negative charge. Okay, so this is a solid crystal of water. And once it's entered into the water, you'll notice that the water molecules pull apart the chlorine. So now the negative chlorine atom is attracted to the positive hydrogen atoms because opposites attract. And your positive sodium atom is attracted to the negative oxygen atoms because, again, opposites attract. So because opposites attract and sodium and chlorine have charges, then they are pulled apart in that manner. So opposite charges attract. Okay, so as water dissolves, the sodium chloride crystal, the part of water that surrounds the chlorine atoms or ions, well, here's a chlorine ion, and the particles that surround it are all the positive ones, which we said was hydrogen. And what part of water surrounds the sodium ion? Well, here's sodium, and the particles surrounding it, oxygen, 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 and they are all negative. Okay, moving on to the right side. The rate at which something can dissolve is telling me basically how fast that solute dissolves. So the rate of dissolution tells me how fast salt can dissolve in water. It tells me how fast sugar can dissolve in water. It tells me how fast a solute dissolves in the solvent. So what are some things that makes a solute dissolve faster? So a lot of times if you pour sugar into your tea, you don't just let the sugar sit there, you agitate it. So in other words, you're mixing it, you're stirring it. Okay, if you just let it sit there, it's going to take a very long time. So you typically grab your spoon or a straw and you stir it up, you agitate it. Another factor that affects the rate at which solutes dissolve is the size of the particle. So the smaller the particle sizes, the faster they dissolve. So if you've ever tried to dissolve a cube of sugar, it takes a long time to dissolve. But when we put in our granulated sugar, or even if you were to put in powdered sugar, it would dissolve much faster because the particle size is much smaller. So here, if we're looking at crystalline sugar, which is our granulated sugar, or the powdered sugar, you got to think which particle is smaller. And the powdered sugar, if you've ever seen it, it's almost like a dust. It's exactly what the name implies. It's powdered. So those particles are much smaller, which means powdered sugar is going to dissolve faster. And another thing that can affect the rate at which something dissolves is the temperature. The sugar crystals dissolve faster in hot solvents and slower in cold solvents. So if you've ever tried to dissolve sugar in cold tea, you've probably had some success because a lot of us drink iced tea. However, if you were to compare dissolving sugar in cold tea versus sugar in hot tea, you'll notice that the sugar in the hot tea dissolves much more quickly than in your cold tea. So the temperature does play a part. So again, 3 things that make a solute dissolve faster. Agitation. That's not what I wanted. Okay, mixing it up. The size of the particle. The smaller the particle, the faster it dissolves. And the temperature. The hotter the temperature, the faster it dissolves. The colder the temperature, the slower it dissolves. Okay, and what keeps gas solute dissolved in the liquid? So a lot of times, those of us that have drank sodas or anything that's carbonated, you notice that the gas, the carbonation, the carbon dioxide is dissolved in the water. But if you leave it out or open for a long period of time, your soda becomes flat because all that carbon dioxide has escaped. Okay, so inside your soda, you have carbon dioxide bubbles. So what keeps it dissolved longer? Well, if I cool it, by cooling the liquid in the solvent or the liquid solvent, this keeps the gas in my solvent much longer. It allows it to stay fizzy much longer than if it was a hot soda. Also, if I add pressure, to the liquid, so this ties into why if you leave a soda open for a long period of time, all that pressure is released and the soda goes flat. But as long as you keep that soda closed, the pressure is maintained and it stays bubbly, it stays fizzy. So how does temperature affect the solubility of solutes? So if I raise the temperature, so let's do this. If I increase the temperature, then it dissolves faster. Okay? If I increase the pressure, then there is no effect. As far as gas goes, if I increase the temperature, then it is less soluble. And if I increase the pressure of gas, then it is more soluble, meaning it dissolves faster. So temperature, an increase in the temperature, the faster something dissolves. A solid, like the higher the temperature of the tea, the faster the sugar dissolves. If I increase the temperature of a gas, then it's less soluble. As far as pressure goes, if I increase the pressure of a solid, there's no effect. Pressure doesn't affect the rate at which sugar dissolves in tea. But it does affect the rate at which gas dissolves. If I increase the pressure of a gas, then it dissolves much more rapidly into my liquid. So again, look over the notes on the front side. Look over your notes from the last couple days. All of that material will be on the quiz tomorrow, Friday.